Hi. In the last video, we looked at a simple language to describe deformable bodies, and we're going to use that language to solve the problem here. It involves a French marsupiami, an animal, and this animal is pushing on a 40-kilogram block, and 20 kilograms of the marsupiami, shown here, are going to stay fixed with the 40 kilograms to make a 60 kilogram unit. So the marsupiami is pushing on the 40 kilogram block, and roughly half its mass is staying with the 40 kilograms. Then there is a second component, which is the 100 kilogram block. Here it is down here. And while the arms of the marsupiami are pushing on the 60 kilogram unit, the feet of the marsupiami are pushing in the opposite direction on the 100 kilogram unit, and roughly 20 kilograms of the marsupiami is staying with the feet region, shown here. So we now have a 120 kilogram unit. And there is friction between the magenta and the aqua units, but the two of them sit on ice. So this is ice and is frictionless. So let's set up the free body diagram. The marsupiami is applying a force through the arms of 20 kilograms per meter second. So I'll show that here. Meters per second squared. Resisting that is the friction from the aqua block. So let's show that here. F fric. And the overall acceleration of the 60 kilogram unit is to the right. I'll show that here. Then by Newton's third law, if the magenta region is feeling F fric pointing to the left, there's an equal and opposite force on the 100 kilogram block the other direction. There's F fric. And now we can use our language of deformable bodies to figure out the force that the feet are applying. The marsupiami, the deformable part, we're going to consider massless. So what do we know about this massless marsupiami? It is applying a 20 kilogram force, shown here, and therefore by Newton's third law, the massless portion is feeling in the opposite direction, a 20 kilograms per meter second force, but we know it's massless, and therefore the sum of all its forces have to cancel out. And so therefore, if the arms are feeling back 20 kilograms, the feet must be feeling the exact same amount going in the opposite direction. I'll put that here. So we can get this because the deformable body that we're treating is massless, and so all the forces have to cancel out. And now we can figure out what the force that the feet apply to the aqua region by Newton's third law. It's equal in opposite direction, so I'll show that here. At 20 kilograms meters per second squared. And now when we look at the actual force equations, we'll see something very interesting happens. First, let's look at the 60 kilogram unit. So the 60 is accelerating 0.1 meters per second. And moving in the same direction is the 20. And in the opposite direction is F fric. And so that's the equation of motion for the 60 kilogram unit. And now we can look at the 120 kilogram unit. The 120 kilogram unit is feeling an acceleration in the opposite direction. So A120, and that is equal to, and this is very interesting, in the same direction as A120 is the 20 kilogram, so 20, and the opposite direction is the F fric. There's no other force because it's on frictionless ice, and we see that the two forces for both the magenta and the aqua region are exactly the same amount. And this is important because that means that since the aqua region is twice as massive, its acceleration will be half as much. A120 is 0.05 meters per second squared, while A on the 60 region is 0.10 meters per second squared. And that tells you that the aqua stuff, its acceleration and therefore its velocity is 2 times greater than what the bottom is feeling. This is true for both the acceleration and therefore the velocity, since acceleration and velocity are proportional. And that tells us then that the important conclusion, which we knew should be true, is that momentum is conserved. Momentum is mass times velocity, and in the upper region it's half as much mass, but it's moving twice as fast, and it's in the opposite direction. So the sum of these, the changes of the momentum, the sum is 0, and therefore momentum is conserved. And we could get this conservation of momentum because we've developed a very useful language for deformable bodies.